we see here the small pendulum. This is a red Christmas tree ornament, that's all it is. We've hot glued the cap on and filled it with water. It has the convenient property that when it's filled with water, the cap on as it is here, as you see it, it's very nearly 100 grams. Now this ornament is supported from the ceiling by a string whose length I can measure. Or if I want to get the effective length of the pendulum, I can let it swing back and forth and time it for a minute or so. That's not swinging very well right now because of some things that are attached to it. But by timing it, I can determine its length because there's a definite relationship between the length and the period of the pendulum. If I time it for 100 cycles, let's say, divide by 100, I get the period, and from that I can determine the length. That is the effective length, and then we're going to use the mass in the usual manner to determine forces. Okay, so the point is now, I've got a friction car on an incline. What happens when I let the friction car slowly move down the incline? I want it to move slowly because I don't want its momentum to pull the pendulum any further than it will go. Remember, the friction car doesn't move backwards very easily. It's got a spring in there, and if momentum carries it beyond the balancing point here, it's going to catch itself with that spring, and we're not going to get a very accurate determination of how far the pendulum is displaced. Now the point is that if I increase the slope gradually of this ramp, the pendulum will displace more and more. Now, if I increase the slope too much the way things are set up right here, of course the pendulum hits the edge of the ramp, and of course we don't want that. We could use a longer string, but I wanted everything to be nice and visible, so I kept things fairly short here. So the point is that the cart will accelerate down the incline, and if I change the incline, I changed a little too fast there because momentum carried me. I really don't want momentum to have anything to do here, so let's try this again. Let's start on a level. Now I'm going to just kind of jiggle the incline so that the cart doesn't stick and then start moving all of a sudden. And we can see the pendulum being pulled over as the incline gradually, increases. Now something caught in the wheel there, and you're going to have to deal with a little bit of that. I can put a scale here, a ruler, some kind of a scale. There's a little ruler attached here, so that I can determine how far the pendulum displaces. I can return the pendulum to its equilibrium position. And read the position on the scale. The scale should, of course, be right next to the pendulum and right next to the pendulum string. And you've been through the pendulum experiment, so you know how to do these measurements. Okay? So there's the setup. Of course, we measure the two ends of the incline, and we want to measure those using one of the line levels and the shelf standard balance. We place the level in the balance, and we get this level, and then we measure the rise for the run of the ramp. And from that we can determine the slope of the ramp for each pendulum position.